Okay, so welcome back to the final session of the day. And we are going to have our final keynote for today. And in this case is Professor Torsten Schaub from the University of Potsdam, and Potasco Solutions, right? So a company, yes. And Torsten is going to be talking to us about knowledge-driven artificial intelligence. So please, Torsten, take it away.
Yeah, thanks, Guillermo, and thank you, everybody, Sasha in particular, for inviting me to the event. Actually, I was planning to come because I'll be going to Melbourne anyway in 2 days. But then actually with the company, we had an audit, and that actually broke a bit my travel plans. The other thing is, originally I wanted to talk a little bit more about how logic actually impacts our applications in industry. But then I thought you guys are actually, you had a packed day. And so I thought perhaps I'd rather give you some more playful things that you may enjoy and also take away with you. So let's get started. So this is more or less the outline. It looks a bit packed, but I will more or less try to stay a bit on the surface and not dig too deep in order to give you more or less an overview of things that I find important and that you actually might find useful in the long run. So motivation. So this is actually something where I think it's an old thing. It's more or less when I started my undergraduate studies, I came across Prolog, and that was also a bit the vision. So the thing is, if you have traditional software development in computer science, well, you have users and they use programs to solve problems, and they are mapped on a computer. The important thing here is that actually this program solves two questions, more or less. What is the problem? It has to know that, and of course, how to solve the problem. Actually, in German, we have this expression Lösungsweg. It's path to a solution. That's more or less what the programming calls. So anyway, if you program more or less, you exercise control, and the program actually mainly is about how to find a solution to the problem. Now, in the, let's say, knowledge-driven way or declarative way, you separate these two things in the sense that you have one part, the knowledge, which only describes what the problem is. And then you have a generic system, a solver, that knows how to solve a class of problems of a certain class. In our case, these are mainly combinatorial search and optimization problems. So in the same way as a computer, and let's see what am I, as a computer is something generic, these solvers are also something generic. They know how to solve problems, and the only problem-specific part is here the knowledge. And of course, here the scale is completely wrong in the sense that usually I think you would only have to draw a line here for the knowledge, because normally, even for applications that we have in industry, the specification is super succinct. Give it a page or two, right? And this is actually what makes this also more and more attractive, also for industry. Okay, but what you get with this actually is that you do not necessarily need computer scientists anymore. More or less, such an approach actually abolishes the need for programming. Well, of course, someone has to sit down and program the solver, of course. But otherwise, for posing the problem, the optimum case actually is that you have an expert at that point. And this expert actually knows about the problem and is not necessarily a computer scientist. And actually, we have actually examples of such things in our industrial day-by-day thingy, where people take up the technology and then try to write a logical specification to solve their problem. And there are cases, for instance, one with a southern Germany company that is doing mechanical engineering, where they were measuring. Actually, the fun part was they got this idea, and the mechanical engineer did this specification before COVID. And then, of course, contact broke up. And then after COVID, they said, oh, look, we were able to measure. We saved 31%. We increased our production by 31%. And these guys are actually listed on DAX, which is the highest German stock market. So you see a little bit, logic really has an impact there and makes a difference. So, okay, so what are the benefits of this, right? Again, think of this just as a specification in your preferred logic, but I, of course, have my preferred logic, and I will talk about this later on. But what you get is, of course, transparency. So things are readable, more or less. And of course, you all know that logic, one motivation for logic is that it is close to natural language. And of course, nowadays, we can even translate the knowledge that is there to natural language. And you could imagine that you have a shift planning system and with different rules, and then you translate this to natural language and give it to the union, and then the union actually can read and be informed about the behavior of the system and can even give their opinion about this. I think this is a super cool thing, in particular now with all these machine learning thingies where transparency is not necessarily at stake. Oh, it's at stake, but it's not really necessarily easily provided. Flexibility, that's the other big unique selling point of logical approaches, is because we have actually quite a few customers that do never sell a product twice. So for instance, they fabricate, again, mechanical engineering, a large machine. These are all customized. Same thing, we are doing shift planning in hospitals, nurse scheduling. And there as well, each department of each hospital has other constraints, views things differently and so on. So you more or less have to come up with a customized specification every time. And this changes over time. And again, it's super easy to do this if you have a high-level specification, a high-level logical specification. And think of milk or whatever, where this is much more complex. Of course, then you have maintainability, reliability. If you want, actually, of course, you can prove that things are correct and complete. But to be honest, only the academic problem that we have been dealing with, where we could even attempt this because there was a specification. Usually the real problem of applying this type of technology or logical specifications in the real world is that people, even the experts that have been dealing with the problem for 20, 30 years, they cannot express their problem. It's really, really hard, and it takes quite some interviewing techniques to get the knowledge, and then in the end, you never know whether you're complete, right? Okay, then just briefly, more or less, on the solver side here, these solvers are generic, they are efficient. If you want, they are optimum, and they're open source. They're freely available. And actually, what I will not talk about this very much, but I think most of you have heard about satisfiability testing, and more or less we use the same technology, just that we don't use classical logic. We actually use an intermediate logic, which I will talk about a bit later. And more or less we use this for knowledge representation, and there is of course a modeling language, unlike, for instance, those of you who know SAT, where it's the input language is Dimex, and you have to care about producing this format by yourself. Okay, so this is a bit what is there. And then the question is, does it really have an impact? And this is, of course, one of my favorite slides at Siemens. That's actually Siemens Austria. They measured the impact, and this is a bit more generic in the sense that it didn't only look at our technology, but constrained technologies. And in a way, this includes this. And over 25 years, what was the impact compared to approaches in imperative languages? And that was, let's say, they looked at this for 25 years, and this is a paper that already dates back 10 years almost. But they could measure that they saved 80% of maintenance costs with such an approach, and 60% of development costs. Again, not fully representative. It was, of course, for knowledge representation and reasoning, mainly when it came to configuration problems. But these guys at Siemens, they configure also the big things. They configure entire tracks in railway stations and the wiring for this and so on and so forth, right? So this is not really small stuff. But it's really nice to have such a slide to talk about and actually then show to people the impact of these things. So what our logical formalism, sorry, I'm still getting used to my iPad here. My logical formalism of choice is ASP, answer set programming. And I have no clue, actually, how many people of you have actually heard about this, because this could, somebody, so who raises a hand? Yeah, actually, I can't really zoom it, but I think this was John, right? Yeah. Anyway, so now I messed up my, where's my screen? Oh, I messed up my. I'll be back. So here we are. Okay. Anyway, I have to accept that we can't interact that much. Anyway, so ASP is a formalism that more or less is a knowledge representation form that rests on very strong logical foundation, and I will come to this in a second. Let me first talk a bit about ASP. So if you can look at this from different sides, right? On the one hand, you have a logic that gives the foundations of. On the other hand, things are used to solve combinatorial optimization problems, and hence you more or less confine yourself to a decidable fragment that is in NP or sigma P2 or whatever. But that's more or less where you end up. But the real benefit of such an approach is that since you have a logical language, that you're really good when you need domain knowledge to come into the process, right? This is really the unique selling points of ASP compared to other solving paradigms. Well, I guess you mostly know what this are, but more or less, it's all about solving first world problems where you have to make many decisions under constraints. And this is not really far-fetched in a way. I think most of you do this every morning when they solve their Sudoku in their newspaper. So Sudoku, I think, is a good example. You have to decide on each place which digit to put, and then of course you have the constraints on the line, the column, and the subtable. But this is more or less the same problem as timetabling, nurse scheduling. And in a way, it doesn't matter because what really delineates the set of problems we can do, they are NP problems or sigma P2 problems, or if you want to be really specific, plus optimization, you can go up to delta P3 or so, right? So this is more or less what the solvers can do. Question is, of course, what about industrial problems? And that's a bit where we moved. And these are some of the problems we or other people in our community face. And so these, the ones that I highlight now in yellow, are the ones we were doing, which we were doing either in our academic group or in the company. So those of you who use Debian and Ubuntu, who want to have fancy configurations, they actually use Klingo, our system, for configuring their system. So one of our biggest customer is Kronos here, which are doing machine and plant configuration. They're actually the world-leading company in bottle filling. So those of you who had a Coke or another soft drink today, presumably it was filled by a machine from these guys. Then we've been working with Swiss Railway quite a bit, and also with Siemens. But the interesting thing actually here is problems where this was used, but with our systems were used, but we were not involved. And this was actually the radio frequency auction in the States in 2016 and 17, where actually I just learned about this afterwards. But you can imagine actually what it means, right? So an American federal department uses a university software, just download this from the internet and esteem it robust enough to run a 20 billion business, right? Because that's in the end what happened here. So the idea that this was an auction in two directions. They more or less bought frequencies from radio stations, and then they auctioned them off to radio stations and to mobile telephone providers, and in order to also to avoid interferences. On the other hand, I have to be honest here. So they did not really use the modeling language and ASP, really the advantage of this, but they used the solver. So more or less, they used a solver portfolio, to be precise, that had two solvers, which was our solver, and a local search solver from the University of British Columbia. So anyway, we didn't see a simple penny for that, but it's always a big satisfaction just to talk about it, right? So, but what you see a little bit is that this is a bit this, I would say, let me say success story. So I was just thinking this morning under the shower what my connection is to the Australian logic community, and actually this is basically due to John Slaney, who I met in 1990 or so when I was a grad student, and who then in 1997 invited me for the logic summer school in Canberra. But at the time when I gave a talk there, right, this was still about well, is Tweety is a penguin, and the penguins are birds, and do they fly or don't they fly? And you have Nixon, and a lot of discussions were still going on about capturing the phenomenon. And so, having moved that far in I don't know, in 20 years now, is quite amazing, right? And I'm very thankful that we were able to do that. But it's more or less, it's something that is deeply rooted in logic and the phenomenon of dealing with incomplete information, then pulling this out into really robust, performant solvers that are actually used. Okay, so this is so far about this. And what you get with ASP, again, is you get a high level and a pretty versatile modeling language, high performance solvers, and qualitative and quantitative optimization, even though I won't be talking about this today. Okay, now let's briefly come to the foundations before we start the fun part for you guys. And this is a bit to connect it to the logical roots. Perhaps before I start with this, again, some historical remarks that may be of interest for you guys. So Vladimir Lifshitz, one of the founders of ASP, Stable Model Semantics, has a paper that keeps changing its titles. So I think the last time I checked, it was about 13 alternative definitions of stable model semantics. And of course, what changed over time was the number of alternative definitions. And unlike classical logic or other logics that have really deep roots, right, that go back, I don't know, to Boole and so on and so forth, or even, let's say, the Greeks, it doesn't really matter that much. But this phenomenon of dealing, for instance, with incomplete information and handling this was really needed foundational work. And of course, what people did in the 80s and the 90s in AI, and again, John, I think, was working on that as well. AI was largely, a big part of AI, symbolic AI, was dominated by automated theory improvers. And of course, first order logic was the logic of choice at the time. And accordingly, also people who then wanted to do, let's say, non-monotonic reasoning or deal with incomplete information, put themselves in the context of first order logic, which of course turned out to be super difficult, right? If you have an approach that is not there's only semi-decidable, and then you want to do inference about non-derivability, that's super hard. And I think the real breakthrough happened when people realized, let's give up on this infinite domain thingy. Let's concentrate on finite domains, and then more or less let's say have a first order length, but use propositional things that are decidable in the end. And of course, the people in SAT went exactly that way. I remember beginning of the 90s because, again, I grew up in an automated theory improving group of Wolfgang Biebel, of course, hardcore first order theory improvers. And I remember when Kleine Bühning, a colleague in Paderborn, had the first SAT competition, they were all mocking these guys. Oh, they're looking at propositional logic. Oh, well, they were overtaken 10 years later, right? So it's quite amazing how that happened. Anyway, so this is just to say that it took decades to find foundations and principles and to identify the canonical approaches in that. And someone has to say that the canonical approach in non-monotonic reasoning in the mainstream is clearly stable model semantics and well-founded semantics. And the interesting thing is, they have a very close connection, because well-founded semantic is polynomial, and you can more or less interpret this as what you get in propagation. And then if you then do search, then you get stable models in the end. Okay, anyway, but again, this is now talking about algorithms and redux and stuff like this. It took actually until the 90s, until David Pearce, and I think we have to be really thankful, he really nailed it down what the logical foundations are. And let's just look at this now. So where we don't have to look at redux and other meta-mathematical things. Okay, first of all, let's take it slow. Open and closed world reasoning. I think that's all more or less preaching to the choir. I can go through this perhaps a bit quicker. In open world reasoning, if something is unknown, you have to assume all the values. Again, in a Boolean setting, this is still okay, but in a setting where you have integer variables, and if a value is not known, and then you have a copy of each solution for each value of this variable, that blows actually things up quite drastically. But anyway, then when you do closed world reasoning, while you normally have a default value, and normally coming from databases, the idea is then if you do not know a statement, then you set it to false. And again, with integers, that's a bit more delicate, but it's more or less the same thing. But the question is, of course, what do you get here? Does it really pay off? Well, somehow you have to say in a company, right? It's very obvious that you want to have closed world reasoning, even at university, right? So only, and we suffer from this every time, right? Only the students, more or less, only the students enrolled in the class can get a mark. And if you're not enrolled, even though it's unknown, well, it's assumed to be false, right? We all know that. So then, of course, you have the monotonicity, non-monotonicity distinction. But with non-monotonicity, you get things. You get, what you can do is you can actually formulate defaults, because you can say something like a variable takes a value unless it takes another value. And of course, if then the value comes, then this has to be overwritten. So this is something that you can do. Another thing that also works well, you can formulate reachability. You don't have to go to a higher order. You can do this actually here in ASP right away. And this is actually a sneak preview. This is basically the constructive notion of the logic that allows you to do that. And what you have as well. So for instance, if you compare SAT with ASP, if you do not extend the language, that's the important prerequisite, you are exponentially more succinct, except if certain assumptions in complexity theory break down, right? So of course, you can always encode things with the Zeithin translation and something else, and then you're in the same complexity class. But if you do not extend the language, you're exponentially more succinct, thanks to the non-monotonic flavor of things. Okay, so, and in ASP, actually, what you get both open and closed world reasoning, and you get more or less open world reasoning for a variable. You just add the axiom of the excluded middle for it, and that actually is what is called the choice rule. And then you can declare this variable as under the open world assumption. Okay, let's just look at this a little bit with some toy examples. Let's say we have A and B in our alphabet, and we have a fact. We have the fact A, just super simple. Then we have three classical models. When I write models, I just mean classical. We have one minimal model, and that is what we would get in the database. Of course, A is true and B is false. And you also here have one so-called stable model. That's what you have in ASP, where A is true and B is false. So there you don't really see actually a difference between the minimal classical models and the stable models. Now let's take a slightly different example. And here we have not just a fact, we have actually a rule. So, oops, I'm so sorry for that. Go away. So here we derive A if we don't have B. And here the important thing is actually, of course, in classical logic, you can translate this to A or B, right? And accordingly, you get these three models. And if you have A and B, then you have two minimum models, A and B. But somewhere in ASP, just as the old-fashioned default logic or prologue or whatever, this implication is not a material implication. And you only get the model where A is true. And there is no chance, actually, if you take the implication serious, there is no chance to derive B. And so there is no model where B is true. And actually, this already smells for many of you, right? Like an intuitionistic approach. And actually, that's where we will actually end up, right? That we have an implication here that is more or less working in the direction of the arrow. There's no contraposition. There's no reasoning about cases. It's really is something that where you only talk about derivability in the direction of the arrow. And then logic programs are formed in the way that you have here. This is actually, you may know this from prologue or from other systems. This is an implication. Then you have conjunction here. Here you have negation. And then in this way, you form rules. And yeah, and then what you get in the stable models, and this is now a shallow definition, is a stable model is a classical model, but importantly, each atom that is true has a proof. All right, it's true in the sense, but it's not only true, all the true atoms have a proof. And this is a proof more or less from the facts with modus ponens or whatever to the atom. That's the idea. And now logically, and now more or less we come to, if I manage to handle my iPad correctly. So we then, and this is now we come slowly to HT. And this was more or less the discovery of David Pearce, who more or less discovered that actually what you do there in stable is nothing else that you take the logic of here and there, or in a three-valued sense, G3 of Gödel, and you look at the minimal, you have a minimal model construction on top of it. And this is interesting also in the sense that some of you may remember John McCarthy proposed end of the 70s, right, and published in the beginning of the 1980s, and so circumscription. And circumscription does something exactly similar. It takes classical, actually at the time, first order logic, and takes the minimal models of it. Very, very, very classic and very neat and approach. And this more or less is more or less exactly the same, just that you exchange the base logic. You don't take a classical logic, you take an intermediate logic here. And well, those of you perhaps you're not so familiar with the definitions, let me briefly run you through it. So you have a propositional logic in the language more or less is not extended. And then with here and there, you have very simple Kripke structure. You have two worlds, the here world and the there world. And you can, from the here world, you can see the there world. And then, of course, as common in constructive logic, everything that is true here is also true there. And this, of course, is simplified here so that our models are only sets of the true atoms. And that's more or less it's if you like it, I think you know that yourself, right? It's the strongest intermediate logic before you reach classical logic. You could actually do the same construction with richer logics, and David Pearce was investigating that, but that's the simplest one that does the trick, and that's also why in the end the definitions are done with this one. Yeah, so then in H, actually you have it represents the provably true atoms. In T, in the there world, you have the possibly true atoms, and everything beyond T are the false atom. And this way, actually, this Kripke structure with two worlds can be seen as a three-valued interpretation. That's actually why it's also very close to Gödel's G3. Okay, and then well, there's entailment and blah blah blah, and then of course you have the satisfaction relation, and here you actually see that the modality here more or less is implication. That is, you have to check the condition for the implication in both worlds, in the here world and the there world. And as a side effect, and this is more or less curious because, of course, I think a popular guy, actually, some of you may know Toby Walsh, right, who is in Sydney, and he kept saying, all this non-monotonic stuff is so complicated because of the negation. But at the end of the day, negation is a secondary operator here. It's defined. It's a defined operator in terms of implication. So more or less, with this logical characterization, what neatly sees actually it's the implication that runs the show and not really the negation. Okay, then, well, you have models, but that's all classical. And then let me just skip this because I think this is something that you know anyway, right? So once you are behind negation, you get classical logic, and that's where you have your tautologies. And then you have the minimization on top of the models, and these guys are called, well, by David Pearce, equilibrium models. So you have a total HT model, and then it's an equilibrium. Well, if it satisfies the formula and it's minimal, so you cannot find a model that has a smaller here world that is also a model of the formula. And this is now exactly a stable model. Right, so this is more or less the logical characterization of this. Good. So this was more or less what I wanted to show you about logic. And this, of course, is a blessing, right? Because now we work on temporal extensions of this. Actually, we have been in touch with Sasha on that, right? Because you can now just merge the logics, and you can take LTL or dynamic logic or whatever, merge this with this logic approach and study the logic or do other things. And it's so nice that you now have a very, I would say, very logical and light foundations that you can manipulate. Okay, now let's come to the playing ground now, and let's see a little bit what we now can do with this. So this is more or less the workflow in ASP, right? You have a problem, you model this as a logic program, and this, of course, is a misnomer. It's not a program, it's a specification, right? But the important thing is you take the problem and you make it precise here. Then this grounder, so here you still have first order variables. This grounder replaces all of them in a systematic way, that at that point you have a propositional representation, and the solver then computes the stable models or the classical models or whatever you want, and then they are interpreted up here. So this is different from SAT solvers, right? Because in SAT, you only have the solver, and you have to start from your problem and map this onto the input format, which is actually a Dimex format, lines of integers, right? And there is no modeling, no knowledge representation, and so on involved. So this part here is really, also the modeling part, is of course what makes ASP here a bit distinct. Okay, so here's just a few language constructs to show you what you can do in the language. I'm so sorry. So of course, here you have the facts. These are the rules, implications, conjunction, negation. Here you have conditionals. This is a type of a very restricted quantification. So what will happen is this construct will produce a conjunction of instances of Q, and it will produce an instance, or it will substitute X whenever X is also satisfied for R. So, and logically, the logical way to view this is an implication, is a sub-implication that you do here. Then you have disjunction, but keep in mind, since we minimize, this disjunction is minimized as well, and this is actually a source for going from NP to the second level of the polynomial hierarchy. Here you have integrity constraints, which more or less, well, logically just means if this condition is true, you get a contradiction, right? So it must not be the case that there is an X for which Q and P is satisfied. And now we come to interesting modeling constructs. For instance, you have choice rules where you say, well, if you fix your Y, you create a set here, the Y is fixed for all the X that run over Q, and then you get a set of instances of PXY, and you have to select at least 2 and at most 7 of them. And this is super handy actually when you want to describe choices, right? Like if you want to configure your PC, right, you want to have at least many hard disks and at most that many hard disks of a certain vendor and blah, blah, blah. That is really, really handy. And it is not just for counting, but you can also do this for summing and so on. So these are more or less the object level, the language part, and then you have on top of this multi-objective optimization, where you can say it's equivalent whether you do this with weak constraints or minimize statements, where you say, oh, I just extended this guy here with this cost here, which says, oh, if you violate this, if there is an X for which Q holds and an X for which P holds and C is true or whatever, then you pay this price, and that's more or less the same that happens here, right? Okay, so these are more or less the basic language constructs. Let's look a little bit what we can do with it. And I just chose a pretty classic one, traveling salesperson. I think you all know that, so let me just go on. And so the way we formulate this is more or less we have a problem instance and a problem encoding that more or less fits all possible instances. So here, again, I give you authentic code here, right? Nothing, no cheating, no abstraction here. You have more or less a graph, which are cities, right? You have 4 cities, A, B, C, which are all facts. I just put this now in one line. And then you have roads between them. So for instance, here there is a road from C to A and the distance is 35. And our salesperson actually starts in the city A. Okay, now an encoding. And this is now not the most efficient or whatever one, which is a bit funny to say because it's a declarative formalism, but nonetheless, you can write equivalent encodings that are more or less efficient. Okay, so here the idea is more or less the following. So actually, this encoding has more or less, from a methodological point of view, 2 parts. It has the upper part, which is the generator, and the lower part, which is more or less the tester. So think of it as an NP as an NP problem where you have an oracle. This is more or less your oracle. So you just look at all the connections of roads. You don't care about the distance. You say, oh, if there is a road between X and Y, I may choose to travel on this. And the choice is where there is no at least and no at most. So you can freely choose. And the funny thing actually is, such a choice is actually logically the law of the excluded middle. You say here travel XY or not travel XY. So you can choose. Okay, now what more or less from again methodological point of view, when you start looking at the rest, you have a solution candidate at your fingertips. And this is super different from programming, right? So everybody who programs in Python or C++, they construct something. Here the idea is you have a guess, And then you work with this guess. And the only thing that happens here, you have guessed something, and then this guy is analyzed. You see, this is more or less everywhere here where you analyze this. Now, these two rules here are an encoding of reachability. You say, well, if you start at X and for some reason in your guess you decide to go from X to Y, then you also visit Y. So you more or less look, what can I, with these rules, what can I visit from my start node with my guess? In the same way, recursively, if I derive that I can visit S and my guess contains the travel from X to Y, then I also visit Y. And now you have a guess and you know what you can visit with this guess. And this integrity constraint then says, it must not be the case that there is a city that you're not visiting. So up to here, more or less, you enforce that really your path really goes through all the nodes in the graph. And then what you say here, and actually one of these guys would be enough, is that there must not be a city that you visit 2 times or more. There cannot be more instances where you are at X and you go out of it, and the other one says there cannot be 2 or more travels from going into X, right? Where you have 2 Ys where you go into X. And this so far more or less gives you a Hamiltonian cycle. And then if you want to make this a traveling salesperson solution, then you have to optimize. And I do this here with this reconstraint, which says I pay for the violation of this constraint. And this is more or less the distance here is what I pay. And this way I get a minimal solution. Now running this, I just do this now here on a shell, right? So Klingo is our ASP solver. The TSPLP was our problem instance. The cities was the encoding. And then you run that. The system finds the first solution. Then when it found the solution, this is now branch and bound, then it adds a constraint that the next solution must be better than 100, which was the quality of the first solution. And so you enrich your problem in that way. Then it looks for another solution and it finds one that has a value 95. Then you add a constraint that the next solution must be better than 95, strictly better than 95. And you don't find one, and this tells you that the last solution was optimal. Right? So this is actually how then optimization works. So I hope this gave you a bit of a flavor. And of course, again, ASP is something that grew out of knowledge representation and reasoning. Hence, it's not just about satisfiability. You also want to be able to enumerate solutions, projected enumeration, calculate the intersection, the union, to do optimization. And of course, you can also combine these guys. You can easily, I don't know, compute the intersection of all optimal models. Or you can compute the union of all optimal models, and everything that is not in the union must then be false. And this actually comes in very handy also in applications. Okay, then at work. So just to give you an idea on what type of problems we were applying these things. I think I was already mentioning, for instance, shift planning, train disposition with Swiss Railway. We do a lot of configuration, product configuration, machine configuration, production sequencing. Nurse scheduling is just another type of shift planning. Our university now starts to use it for timetabling, but also to formulate study regulation. That's all pretty cool. So this is just to give you an idea what we can do beyond the traveling salesperson problem. Okay, oops, I'm still in my painting mode. So one thing when I was preparing my talk, I decided a bit to change it, because I now originally wanted to show you how we integrate now integer constraints into the system and how the logic of here and there with the denotational semantics does it. But then I realized that you guys, it's now close to 6 p.m. And perhaps you don't really want to get so technical. So I'd rather show you something to play. The thing is, you have seen the initial workflow, right? And it turns out that with ASP, if you sit together with someone who has a problem, a customer or an academic friend, I usually say, well, let's meet, bring a toy example, something that you can solve with paper and pencil, or that we can solve on the blackboard. And people arrive and we do this, and it usually takes an hour or two, and you have a first logical specification, a first ASP program that does it. Okay, then of course, everybody gets excited in the room. You push the button, a solution comes out, and well, the jaw of the friend drops. Oh, that's completely wrong. So why is it wrong? Blah, blah, blah. You hear the reason, but then the answer is, oh, you didn't tell us. Of course, then you specify this and you have a few iterations. At some point, you more or less get a solution. But still, what you've seen as well, the output is text-based. And in particular, in a world with in industry or so, nobody wants to see a text-based output. So this was then actually sparked by our industrial applications and with customer relations that we said, we need a visualization. We need something where we can also in 1 or 2 hours produce a visualization of the result. So if we have someone sitting in the room who only cares about visualizing it, either visualizing it or even creating a user interface in 1 or 2 hours. And at the same time, we create a solution, a logical specification. We also can create the visualization of it. And this is actually what we did, and it worked out really like a charm. And let me just show you this. Again, this is our workflow from the beginning. And keep in mind, so far here, interpreting the stable models meant you have the set of atoms that are true in the model, and somehow you have to deal with it. But what did I usually do? Well, I copy-pasted it in my editor. I saw it, looked at it, shit, mistake, have to go back. But it was really, really tedious. Okay, now here's just what we do for ClingGraph. This is more or less how to visualize things. And here we use a graph-based library. So the idea is we want to do Sudoku. And okay, what is a Sudoku puzzle? We have this problem. We do this. We describe this in ASP. Here are some facts. That's just a 4x4 Sudoku. Here we have parts of the Sudoku encoding, right? And then what happens is, again, textual output. We can read it off, but it's very boring. Now, how can you more or less make this graphical easily? The idea is now to say, okay, what we have to, in the end, what we have to visualize is the model. So that's what ClingGraph does. It visualizes more or less the solution of this guy. So you more or less think of, okay, if you get a model, what's the signature of this model, and how can you describe it? And then in the same way as you write a problem encoding that solves the problem, you write an encoding that more or less relies on this guy and that describes the visualization of it. So, and this is the big advantage here of the whole approach, that you do it also in ASP. And actually, to be honest, I was recently at a meeting where I was describing this, and someone afterwards actually stood up. Jesse Hendrik, he's a philosopher from Belgium, and he said this is really exciting for him because he is a philosopher. He has no training in computing, in programming, and so on. And being able to also describe the visualization and the interface in logic, and not to go to a programming language, was a big breakthrough for him, and also making his work more attractive. Okay, so how does that work here? So for more or less here, again, this is for visual, it's more as a graph-based thingy. And this is the visualization that you get, right? If you get a solution. So how does this work? Let me show you now in the same way as you show here part of the solution. Now, how does the visualization encoding look like? Yeah, so here we have more or less, for this, we have roughly four keywords. We have to produce, we can produce different graphs. They can be animated, right? Depending on the library you use. You have here, for instance, this is a graph. You can have really different stuff. You can even for those of you who like LaTeX, you can even produce LaTeX or ticks with this, right? So it's really powerful. And then here's the encoding, and you see what more or less what we describe here, where we give the graph a name. Then for all the positions in the encoding, we generate, because this is what the system wants. And by chance, it's the same predicate name, right? So this is actually from the encoding of Sudoku. This is now for the data here in the visualization encoding. And then you see, for instance, here that so for instance, you fill more or less a certain site with blue if this condition is true, and this is actually what happens here. This is what this formula here does for you. And then, for instance, if you have if you have the value v at position x, y in the Sudoku, and it's not initial, you gray it, and these are more or less the things that were not initially set. You know, these are grayed out, and the others are black, and more or less in the same way. This is just beautification. You make things nice, right? So you talk about the width, the font, but you can do more fancy stuff, right? And here you grab the solution, which is the Sudoku predicate, which each of one says at position x, y, there is a value v, and then you describe here this value has to go inside. There has to be a square, it has to be filled, etc., etc. And now we meanwhile describe entire user interfaces in that way. And those who are a bit familiar with how this works can do this in the same way as one writes an encoding to it. Very, very useful. Okay, what did I not talk about? Just some notes here. So one thing I personally love a lot, and actually that may be also because I started initially with Lisp end of the 80s, is metaprogramming. Because since you have an approach with a syntax, right, you can manipulate the syntax. So what you can actually do is you take your initial program, you turn the rules into facts. So more as you translate program into data, and then you write a meta encoding that describes an ASP interpreter or how you want to do things differently. That then takes that then interprets the control or more or less the language expressions of in ASP by yourself. So you write your own system to do that. So for instance, for temporal stuff, if you want to extend your system, or you want to add explanation to things, or you want to interpret, I don't know, the implication in a different way with a different logic. And then you can just, wherever this is defined, you write some code, and then you do this in ASP. So it's also the meta. So the meta interpreter for ASP is also just half a page, right? Anyway, so you see that I'm pretty excited about that. Okay, otherwise we have this optimization. You can also do heuristic programming, that you can influence declaratively the heuristic of the solver. Then you have all these, you have a very powerful API here where you can do multi-shot solving, which means you create a solver and then you interact with the guy in the long run. You can do theory solving, you can add theories like, I don't know, linear equations or other things. And what we've been doing recently where we're looking at temporal extensions to it, visualization I talked about. And if you feel like this interests you, just go here to our site, potasco.org, where you can delve into this. And of course, there's a GitHub, which is called also just Potasco, where all these systems lie, and you can just download them. They're open source and play with them. Okay, to recap, so the take-home message. Well, first of all, I think what we have with ASP is not just a solving paradigm like such, right? It's really, the modeling is super important. Grounding is something that is more or less paves the way from the modeling to the solving. And funnily, actually, grounders are Turing complete. That's quite funny, because the instantiation process is more actually has function symbols and so on, and actually you can encode a Turing machine, which is funny, right? Because you view it as a pre-processing tool. It's super powerful, and then it hands things over to a solver that decides things and is at the second level at most, right? Okay, so in a way, ASP has these, I'd say these four mothers, right? Databases, of course, if you think the grounding technology comes from database technology, it's about semi-naive database evaluation, logic programming, and non-monotonic reasoning, where more or less the semantic was coined, and logic programming. After all, stable model semantic was initially proposed as a semantics for Prolog, right? And actually it is, Prolog is correct with respect to this, but not complete, because it may, of course, not terminate. Then knowledge representation and reasoning gave a lot of, let's say, principles on the way. So, for instance, John McCarthy coined things like elaboration tolerance. So a form, when is actually a language good for knowledge representation? Well, he was saying, well, if a small change in the world is also reflected by a small change to your representation. Can't do this with C++ or Java, right? So while here on the logical side, you change the facts more or less. That's what it amounts to. And this is still a guiding principle that is super important if you model and you want to take things to industry, right? It's perhaps you don't have to hang this to make it your primary principle, but it's super handy when you want to evaluate good designs. Okay, yeah, technically it's perhaps an SMT, multiple SMT, so but that's not so important. And of course, there is the our Potasco site, and it's lots of fun. And as I said, right, when I was thinking last night and this morning a bit about actually not being with you guys because I was planning to, of course, having met John in 1990 or so, right, and all that took me back a bit to my graduate days. And then I added actually this slide, which so after all, during my graduate day, this book here was lying on my desk, right? It was more or less my Bible at the time. It's Readings in Non-Atomic Reasoning. And you see this Tweety there that really has trouble flying and is not perhaps that reliable. And so in the end, and that's actually I got from our Linux magazine, is now Tweety Unleashed. In a sense, thanks actually to Boolean constraint technology, so the technology that the SAT people boosted, we could build all this up, right? And now we have this Tweety here that is a bit unleashed and needs to be tamed as well. And that ends actually my talk. I hope you liked it. It's always a pity that I can't interact with you guys directly, but perhaps we get something going now. Thank you.
So we have time for questions. Any questions, comments? John.
Hi, Torsten.
Hey, John.
Yeah, in a way, answer-set programming sits in the same universe as constraint programming, except that the constraint programming guys have gone with classical logic as a base, and you know that's good and bad for their program. In a way, the attractiveness is the same. It says, in some ways, it's the holy grail of high-level programming. You know, you don't write a program at all. You tell the machine what your problem is, and it tells you the solution. It's like programming in Star Trek or something, where you don't write a program. You just say to the computer, you know, this is our engines down, and the Klingons are over there, and this and that, and it says plot a course for Gamma 3 or something. And you don't want to know how it did that. But in the constraint programming world, there is the same idea that you write a logical specification and then somehow the magic black box will turn that into solutions. But in practice, when they look at problem like a TSP or something like that, you get to a level where you have to worry a lot about the heuristics, about how you're going to how you're going to achieve some efficiency. I mean, how you're not just going to thrash with, you know, stupid generate and test. And then, you know, somehow you have to break open the black box and you have to write dirty code for real applications. Does anything like that happen in your world here, or you know, can you keep your hands clean all the way down?
No, we can't. But this is again one of the holy grails, right? So, as a matter of fact, of course, you may write two equivalent encodings that show different performance. But so far, actually, when it comes to scaling, it's always a matter of improving the specification, and it's a conceptual thing where you can do a lot. We also have the tools to do parameter boosting, some more or less twitching on the solver side. But normally, so the slogan I usually say also in class is, you can never recover from a crappy encoding. Right? You really have to think a lot, and that's where we put a lot of emphasis in getting the encoding, the specification right. But on the other hand, we see that, and we actually have two. So because actually, I think the role model there, even though it's easier, I'd say, is databases, right? So in databases, you pose a SQL query, and you don't care at all about the efficiency. And then actually there are optimizers behind that do that for you. So, and I think this would be really cool to have, and we are working on that. So in two ways. First of all, we have a system called NGO, that takes a specification and has lots of ad hoc transformations that we know from modeling, that actually then translates the problem in something more, potentially more efficient. And at the same time, we have the Anthem system where we deal with verification. Because actually what you're interested in is not necessarily, well, let me backtrack. So normal equivalence in the logic of equilibrium logic, since it's non-monotonic, does not allow you to replace equivalent subformulas and maintain the equivalence of the whole thing. There you need something like strong equivalence. Cool thing is, something is strongly equivalent in this equilibrium in the non-monotonic approach if it's equivalent in the monotonic approach. So we actually now we just published the first theorem prover on the logic of here and there. So these are the two ways. And my ideal thing in the long run is that we actually have software development tools that you write the clearest, the cleanest, the nicest specification, and then perhaps the system does suggestions, or you modify things. It's a development process, right? And then this is in the background, you have a theorem prover that makes sure that all these logical transformations are actually equivalence preserving. So anyway, to sum up, yes, we have this problem. With us, it's not so much on solver tweaking, but on specification tweaking. And we are working towards that, but it's not yet there. We're not yet there.
I think there are none. So in this, yes, I can't see any. So with this, we close the session. Thank you very much. And thanks the speaker again.
Thank you.
For a round of applause. And thanks everybody for staying up until now.
Yeah. Well,
That's
thank
it.
you.
Thank
Yeah.
you very much.
Thank you, everybody. Bye-bye.
It's going to, oh, the recording. I don't record the part about the correlation of the willing. Yeah. Stop recording.